You remember your childhood home, your first day at a new job, what you had for breakfast this morning. None of that information is written down anywhere physical. It's stored entirely inside roughly 3 pounds of tissue. So how does a soft, biological organ actually hold on to decades of information without losing it? Much of what we know traces back to one specific patient, one surgery, and one genuinely tragic mistake. And more recent research has revealed something genuinely unsettling. Memories aren't as fixed as most people assume. Let's get into it. Let's start with the basics. Your brain doesn't handle all memory the same way. Short-term memory holds small amounts of information for just seconds to minutes, like a phone number you just heard. Long-term memory is different, capable of storing information for years, even an entire lifetime. The process of moving information from short-term into lasting long-term storage is called consolidation. For decades, scientists didn't fully understand how or where that transfer actually happened in the brain. The answer came from one of the most famous and most tragic cases in the history of neuroscience. In 1953, a 27-year-old man named Henry Molaison underwent brain surgery to treat severe epilepsy. Surgeons removed a section of tissue from both sides of his brain, including most of a structure called the hippocampus. The surgery genuinely helped his seizures, but it caused a devastating, completely unexpected side effect. Henry lost the ability to form any new long-term memories at all for the rest of his life. He could still recall much of his childhood, but everything happening from that point forward simply never stuck. Referred to publicly only as H.M. to protect his privacy, he became the most studied patient in neuroscience history. Studying H.M. for decades revealed something crucial. The hippocampus is essential for forming new long-term memories. Without it functioning properly, new experiences simply couldn't get converted into anything lasting. Interestingly, a detailed 2014 post-mortem study found a portion of his hippocampal tissue had actually remained intact. This added helpful nuance to his case, without changing the core, well-established lesson about the hippocampus's role. H.M.'s case also revealed something else important. Memory storage isn't permanently stuck in the hippocampus. Researchers believe the hippocampus acts more like a temporary staging area for brand new memories. Over time, through a process called systems consolidation, memories gradually shift into the brain's outer cortex. This is exactly why H.M. could still recall childhood memories. Those older memories had already relocated to the cortex. It's a genuinely elegant system, a temporary workspace, followed by long-term, more distributed storage. Let's zoom in even further, down to the level of individual brain cells, to see how this actually works physically. Memories are believed to be stored as patterns of strengthened connections between neurons, called synapses. When two neurons repeatedly activate together, the connection between them physically strengthens over time. Neuroscientists often summarize this idea with a simple phrase: neurons that fire together, wire together. This strengthening process has an official name: long-term potentiation, often abbreviated simply as LTP. Neuroscientist Kandel won a Nobel Prize in 2000 for uncovering the precise molecular details behind this process. He famously studied a simple sea slug, since its large, easily observed neurons made the underlying mechanism clearer. His work showed that memory formation genuinely involves real, physical, molecular changes at the synapse itself. Now here's the genuinely unsettling part one mentioned at the start. For a long time, scientists assumed that once a memory was fully consolidated, it stayed fixed and stable forever. In 2000, neuroscientist Kareem Nader published research that seriously challenged that entire assumption. His team found that recalling a memory temporarily makes it unstable again, requiring it to be restored afterward. This process, called reconsolidation, means memories can actually be altered slightly every time they're remembered. In rats, blocking this restorage process with a specific drug could even weaken or erase a previously feared memory. This helps explain why eyewitness memories can shift and change slightly with each retelling over time. This discovery has led to genuinely promising real-world clinical research. Researchers have explored ways to reduce the emotional intensity of traumatic memories during this brief, unstable window. A study published in late 2025 tested this idea in people with PTSD, using brain stimulation timed around memory recall. The goal isn't erasing the memory entirely, but softening the intense emotional charge attached to it. This research is still early, but it represents a genuinely promising new direction for future trauma treatment. There's one more genuinely fascinating detail from H.M.'s case worth covering. Despite being unable to form new explicit memories, specific facts and events, H.M. could still learn new physical skills. In one experiment, his drawing skill on a specific challenging task steadily improved with repeated practice. Remarkably, he had no conscious memory of ever practicing the task at all, despite clearly getting better each time. This revealed that explicit memory and implicit, skill-based memory rely on genuinely separate brain systems. It's part of why you can still ride a bike years later, even without consciously recalling how you originally learned. Quick pause before we continue. Take a guess. Do you think every single memory you have goes through this exact same reconsolidation process equally? Not necessarily. Research suggests older, more deeply consolidated memories may be somewhat more resistant to change. It's still a genuinely active area of ongoing memory research today. Let's clear up a few common myths before we wrap up. Myth 1. Memories work like a video recording, capturing events with perfect, unchanging accuracy. Not accurate. Memories are reconstructed each time you recall them, and can shift slightly with each retelling. Myth 2. Once a memory is fully formed, it stays permanently fixed and completely unchangeable forever. Not true, based on reconsolidation research. Recalling a memory can genuinely leave it open to change. Myth 3. The hippocampus is where all your long-term memories are permanently stored forever. Not accurate. It mainly helps form new memories, which later relocate into the brain's outer cortex over time. Myth 4. Skill-based memory and fact-based memory work through the exact same brain systems. Not true, as H.M.'s case clearly showed. These rely on genuinely separate, independent brain pathways. Let's wrap up with a few fun extra facts. H.M. participated in memory research for over 50 years, until his death in 2008 at the age of 82. He donated his brain to science, and it was later digitally mapped in extraordinary, microscopic detail. The human brain is estimated to contain around 86 billion neurons, each capable of thousands of connections. That staggering level of connectivity is part of what makes such enormous memory storage capacity possible at all. Every single memory you have is quietly supported by this same basic biological toolkit, working constantly. Okay, let's bring this all together. The hippocampus is essential for forming new long-term memories, a lesson learned directly from patient H.M. Over time, memories relocate into the brain's cortex through a process called systems consolidation. At the cellular level, memories are stored as strengthened synaptic connections, a process called long-term potentiation. Recalling a memory can actually make it temporarily unstable again, a process called reconsolidation. And skill-based memory relies on a genuinely separate brain system from fact-based, explicit memory, all from one soft, 3-pound organ that's been quietly rewriting itself your entire life. If this answered a question you never knew you had, that's exactly what this channel is about. So if you enjoyed this, hit subscribe so you don't miss the next one. It genuinely helps this channel grow, and it takes about 2 seconds. Drop a comment and tell me which part surprised you the most. Was it H.M.'s story? The reconsolidation research? Let me know. And if you like this video, go ahead and tap that like button. It's a small click that genuinely helps this channel keep growing. There are hundreds of everyday questions just like this one waiting to be explored. Things about your own mind you've never actually stopped to question. That's what this channel is all about. Toggling your curiosity on, one question at a time. One more thing before you go. Tap that notification bell too, so you actually see it when the next video drops. Next time, we're tackling why flamingos stand on one leg for hours without falling over. It's a surprisingly clever energy-saving trick, and you will not guess the mechanism. I'll see you in the next one.